Okay, so this next type of isomer is called a conformational isomer. And we said that isomers are pretty much the same compounds, but they differ a little bit, right? So how do conformational isomers differ from each other? All right, well, we say that conformational isomers differ in rotation, the rotation of their bonds. Let's write this down. So conformational isomers, these don't differ in connectivity. They're going to differ in rotation. These types of isomers differ in how their bonds are rotated. And another way of saying this is that they differ in conformation. All right, so conformational isomers are going to have their bonds rotated in different conformations. Let's write that down. Okay, so conformational isomers, these guys are going to have their bonds rotated in different conformations. And another way of saying conformations that you're probably more used to hearing is orientation. So conformational isomers are going to have their bonds rotated in different conformations, different orientations. Okay, so before I show you an example of a conformational isomer, let's get one thing straight. Conformational isomers only differ in rotation. They do not differ in connectivity. That means that their atoms are going to be connected in the exact same ways. And I prepared a demonstration for you to illustrate what I mean by this. Alright, so what I mean is, take this compound for example. This is one possible conformational isomer of this compound. Okay, so take a look at this yellow bond between these two black carbons. So pretend that these black atoms of this model are carbons, okay? If I rotate this yellow bond, that's going to change how the bonds and atoms on this carbon are oriented to the bonds and atoms on this carbon. And hey, this might be a little clearer if I turn this model this way. Alright, so notice how if I rotate this bond clockwise, this is going to orient the red atom on the front carbon closer and closer to the red atom on the back carbon. Okay, so if I rotate these, the two red atoms are going to get closer and closer until they get as close as they can get. And then if you keep rotating, they will become oriented further and further away from each other. And with each slight rotation, this is going to produce another conformational isomer of this compound. So hey, this would be one conformational isomer. If you rotated it again, it's another conformational isomer. Rotate again, this is another conformational isomer. This is another one. This is another one, okay? The point is, you guys, anytime you rotate a bond, you're changing how these bonds and atoms are oriented. And it puts this compound in different conformations. So we call these conformational isomers. They only differ in rotation of their bonds, all right? All right, so here's the question that a lot of people have about this. Because if these isomers have the exact same connectivity, meaning that no matter how you rotate the bonds, the atoms are all still going to be connected the same way. So if they have the exact same connectivity, then why do we care about how their bonds are rotated? Why do we care about all these different conformational isomers? Okay, so let's write this question down. All right, so here's the question, you guys. These things have the same connectivity. Same connectivity. So why do we care about these different rotational conformations? So why care about different conformations? And the answer is because some conformations are lower in energy than other conformations. So let's write that down. Okay, so why do we care about these different conformations? It's because some conformations are lower in energy Some conformations are lower in energy than other conformations. And so if one conformation has lower energy, then that means it's going to be more stable than other conformations. So, hey, some are lower in energy, therefore, they're going to be considered more stable. Therefore, more stable than other conformations. And hey, you guys, what did we say is always favored in chemistry? Stability or instability? Stability, right? Things will always go from less stable to more stable. So it's important to identify which conformations are higher or lower in energy, because compounds will exist more often in lower energy, more stable conformations. So let's write that down so you don't forget it. Okay, so let's make a note here. Because compounds will exist most often in low energy, high stability conformations. Okay, so what this is saying is that one conformation can be more or less stable than another conformation. And this is really important to understand because most likely we're going to be dealing with compounds in their most stable, lowest energy state because that's how they exist most of the time, okay? So hey, let's look at some examples of conformational isomers now. And let me just tell you that there are two main situations where you'll be dealing with conformational isomers. One is with straight chain alkanes, straight chain compounds, and the other is with ring cycloalkanes, okay? So let's go ahead and talk about straight chain alkanes first. Okay, so there's two situations where you'll be dealing with conformational isomers. One is with straight chain compounds and the other is with ring compounds, all right? But let's go ahead and start out with straight chain compounds first. Straight chain compounds, okay? Okay, so let me start off by telling you that straight chain compounds can have their bonds rotated in two main types of conformations. Their bonds can be staggered or they can be eclipsed. Okay, so let's write this down. Okay, so there's two main types of conformations that straight chain compounds can be in. One of them is staggered. And go ahead and put in parentheses next to staggered, anti, comma, gauche. And I'll tell you what this means in just a second. Okay, so one main type of conformation is staggered. And this is versus the other type of conformation that a straight chain compound can be in, which is eclipsed. All right? Okay, so what we've written up here is that there are two main conformations, staggered versus eclipsed. But there are two types of staggered conformations, anti and gauche. You can either be anti-staggered or you can be gauche staggered. And we'll see what these look like in just a second. But hey, first do me a favor and write down that there are two types of strain involved in conformational isomers. And these are torsional and steric strain. And you have no idea what these types of strain mean just yet, but you will in a second, all right? For now, just know that the more strain a compound has on it, the higher in energy it is. So a compound is always trying to minimize its strain to lower its energy so it can be the most stable possible, okay? So, hey, now let's take a look at an example.